Hello, welcome to the Stellar session. We have first Jan van Roestel from ISTA giving us a talk about, you don't have your title, but stellar non-transients.
Yeah. Hi, everyone. I'm Jan van Roestel. Indeed, I don't have a title on this slide because I just wanted to show my second thing I'm involved in. Besides at ISTA, I'm also a guest at the University of Amsterdam and project scientist at BlackJam. This is BlackJam. I'm not going to talk about it, but you can ask me any questions about it over coffee or something. What I'm actually going to talk about is my work with ZTF. And I have to say, it's great to be back here at Caltech, where I used to be a postdoc when ZTF started. But it's also great to be back at Hot Wiring, because I realized I was at my first international conference, was 10 years ago, was Hot Wiring in 2016 in Villanova. So it's great to be back in, well, multiple ways. The goal of my talk is really to convince you that alerts are not only interesting for extragalactic transients, but also for all kinds of galactic objects. Yeah, let me just give a brief outline. So first of all, I want to start with, what kind of different data products are we using to study galactic stars? These include alerts, but also other light curves. The second part will be to just give you a very brief overview of all the things we found using the ZTF alerts in the galaxy, in the galactic plane. And finally, my currently favorite topic, how we can use actually negative alerts to do interesting science. And then I'll end with an overview. So the motivation for this talk is indeed this, that both Ruben and Roman will see many, many stars. Of course, Roman will do the galactic plane survey. And Ruben will do the wide, fast, deep survey, which includes at least a little part of the galactic plane. So both these surveys will see many stars, and that's why I thought let's go back to ZTF and see what we actually learned from doing 7 years of ZTF galactic science. So just to show you the ZTF footprint with the stellar density at the background, you can see that depending on where you point the telescope, there's a huge range of stellar densities. I think it's more than 2 orders of magnitudes difference. But what I want you to remember is that depending on your attitude, there are always foreground stars everywhere, and that can be a problem, or I would think it's an opportunity. All right. So just to take a step back and look at what actually varies in the night sky. So I really like this figure. It gives a very nice overview of all the different kinds of variability you might find. Of course, there's the asteroids there and the AGN over there. But actually, at least according to this diagram, most of the variability is the result of stars doing something. Of course, you've got all the supernova that most of you all talked about for the rest of the week over here. But you see there's lots and lots of other kinds of variability. You've got pulsating stars, other kinds of cataclysmic stars like dwarf novae, stellar eruptions, eclipses, rotation, and of course, microlensing as well. All right. So with that in mind, how do we actually study these objects? And the reason I'm asking this question is that if people talk about ZTF light curves, this can mean very different things. This can mean light curves from alerts, light curves from PSF photometry, light curves from forced photometry, and then forced photometry from difference images or science images. So there's many different ways you can use the ZTF images and make a light curve and then study whatever star you're interested in. I just divided it in basically 2 main categories. You get basically the forced photometry, where you kind of know where your star is. You also know what the point spread function of your image is. And with that, you can make quite high accuracy, high precision measurements. However, these typically have a high latency, although that's actually changing quite a bit. Of course, there's also the alerts. You do difference imaging. You basically are agnostic about the location, so you don't need to know where your object of interest is beforehand. And of course, very important is that these are available almost immediately. So with that in mind, I kind of divided stars up in a different way, more phenomenological. For example, you can have stars which are always visible, and they can vary, like, for example, sinusoidally, like here. And that's actually where the bulk of the galactic stellar science is done. Just to give you an idea, we've got lots of binaries, rapidly rotating white dwarfs, Ilaria works on, pulsating stars. And what we basically do, we take a light curve, we run a periodogram, we fold the light curve to the period we found, the periodogram is down here, and then we do the analysis that way. And for this kind of science, it's really the best to use the PSF photometry. However, for the other cases where your star does something irregular, maybe it is always visible as eruptions, or it's not visible in quiescence as repeated eruptions, or it even shows like a single outburst or brightening. Typically, alerts are a good way to study these objects. All right, so with basically a kind of technical review done, I just briefly wanted to look into all the different science that people have done using ZTF alerts. It's definitely not all my own science. And I think one of the most interesting things where you want to use alerts for galactic sources are microlensing events. We do have a few experts in the room, but these microlensing events are basically occur when one star moves in front of the other and lenses the light from a background star. And in those cases, you get like a brightening, which is, for example, seen here. These are very interesting because you can study basically dark objects such as stellar mass black holes, or of course, stars with exoplanets. And for these events, it's important to do to rapidly respond and get higher cadence photometry, for example. These are some people call these the vermin of the sky, dwarf novae outbursts. I like them a lot, but as you can see, they're everywhere. With ZTF, we did an archival search of the alerts, and we found more than 10,000 dwarf novae outbursts. These outbursts happen when a white dwarf that's secreting from a donor star and creates an accretion disk. This accretion disk becomes unstable and brightens the system by up to, well, 5 or even 8 magnitudes. Just some work done by Paula Scotti there, and I also found a few of these. But here the challenge is really like not all 10,000 of them are interesting. We really want to find the more interesting ones. For example, the dwarf novae, where you've got a white dwarf that's secreting from another white dwarf. And these are much more rare, but they basically, or to first order, they look the same. Actually, just a little deviation, but actually when ZTF turned on, we found also these very long duration events, which had rise times of a few months and decay times of maybe half a year. And initially, these were confused as superluminous supernova. But what we quickly realized is that these are actually these dwarf novae, which for some reason have extremely long brightenings and then or eruptions. It's still a little bit unclear what these things are. But with ZTF, we happen to be very lucky. And this one had this long outburst, but also a very short duration outburst. And during the short duration outburst, we happened to do some deep drilling on this field. And there we saw actually a periodic signal of slightly less than an hour, showing that this is indeed one of these compact binaries. So this is just an example to show you that you can even find periodic signal in alert data. Right, just moving on to the X-ray binaries. Of course, these are very similar. Instead of a white dwarf, you now have a neutron star. And this is AT 2019 WEY by a paper by Yuan Yao, who looked at this object, which was in quiescence for a long time, suddenly brightened in the optical and stayed bright for a long time. And if you look here, you see that actually the X-ray brightening happened like a few months later. These objects contain a neutron star or black hole, are very interesting, of course, for stellar evolution, but also accretion physics. And finally, just another very nice discovery by ZTF is this stellar merger, was it? I always get confused. It's Subluminous Red Nova 2020 by Kishale. In the optical, it actually doesn't look super different than these dwarf nova outbursts. If you would have a quick look at it, you might get confused. But the interesting bit here is that it was also brightening in the infrared, and this turned out to be a merger between a star and a planet. Sorry. So there's very different kinds of science you can do with alerts from the galactic plane, and I'm sure both Ruben and Roman will find many more of these objects. For the last bit of my talk, I wanted to look into disappearing stars, so actually negative alerts. So actually, I was very curious because when ZTF does image differencing, it takes a science image and subtracts the difference, but it also does the other way around. And that's a very good way to find things that disappear. So that's what I did. So I took the diff mag pause as false and the dist nr less than 3 and translated this basically any source that disappears but does have a star in the reference image. And this is just what that looks like. So a science image has nothing there, but the reference image does have a star there. This is a very good way, or at least I thought would be a good way to find dipping stars. Well, when you do that, you find a lot of false positives. Excuse me. There's many things that aren't very interesting. I specifically looked at the white dwarf stars because that's what I'm scientifically interested in, and also it cut down the entire sample a bit. So what I did here is basically look at plotted here is all the negative alerts associated with the white dwarf, and this is the reference brightness, and this is the magnitude difference between the science image and the reference image. Basically, objects down here basically fade by 100%. There's many deep eclipsing white dwarfs in here, but there's also many white dwarfs which have a high proper motion. Of course, the position on the science and reference image will not be the same after a few years, and they all start to trigger alerts. So the theory was nice, but there's still a lot of non-interesting objects to remove. And just to show here on the right, if you would make an alert filter based on any white dwarf which triggers more than 3 negative alerts, we still need to look at 40 white dwarfs each month, and almost all of them are not really interesting. There is an exception to that. I did find some very interesting things, and this is a white dwarf which, with here the ZTF data, which basically was non-variable for 20 years, and then from 1 year to the next, it completely vanished for an entire year. And then now it's slowly coming back and might actually be going down again. The other thing is that it was associated with a tiny but significant infrared flare at the same time as it's dimming in the optical. So this is a really interesting discovery, and actually my fishing expedition turned out to be a success. So just to show you what that looks like. So the white dwarf star is there in the middle. This is a time lapse of the ZTF images. And if you look at the data there, in about 2022, the star in the middle will be completely gone for a year. So this is and this is what triggers the negative alerts. Sorry. So what's going on here? So after a lot of follow-up, spectroscopic follow-up, high-speed camera follow-up, we concluded that. Oh, sorry. Wait. Sorry, there we go. We concluded that this is a white dwarf star where a rock came too close to the white dwarf, maybe got tidally disrupted or collided with another rock, and that started a collisional cascade. So we got like rocks orbiting the white dwarf. They started colliding with each other, creating more debris, and that debris started to basically cause a cascade. So, and that resulted in the production of a lot of dust and debris, as you see here in the image, and that completely engulfed the white dwarf star. So it's really kind of an example of what maybe the final fate will be of the solar system. This dimming and infrared brightening wasn't the only sign we saw. this white dwarf also turned out to be one of the most polluted white dwarfs known. So what happens is that material makes it to the atmosphere of the white dwarf. It mixes with the atmosphere. This metal pollution sinks down quite rapidly. So if you detect any metals in the atmosphere, it's almost certainly that there was a recent accretion event. And this one is, as I mentioned, I think the second most polluted white dwarf known. All right, so that's one white dwarf. Another very interesting thing I found looking at these negative alerts is that this is another white dwarf, which again was non-variable for a long time. And then suddenly it started to show a periodic signal. And the periodic signal had a period of 5.9 hours. And it seemed the amplitude of the signal seemed to slowly decay again. This is probably another rock orbiting the white dwarf. So you've got one rock orbiting in the 5.9 hour period. For some reason, it either had a collision or got too close, or it was disrupted somehow. It started expelling gas and debris and gas from its L1 and L2 points. So basically leading and trailing material, which resulted in this very stable periodic signal that slowly decayed over time. So this is probably one of the further stages of one of these collision events where you still have a few remaining rocks that can suddenly just break apart and produce a periodic signal. Again, that was detected using alerts in the ZTF data stream. All right. Actually, there's a few more of these white dwarfs in the ZTF alerts data stream. Some of them actually show very smooth signals. Other ones suddenly become kind of chaotically variable, and then the signal disappears again. There's also events which have a rapid increase and then slowly go back to normal again. And unfortunately, I found all these things in an archival search and not in a real-time search. So it would have been great if I actually found these in real time, or was able to get high-speed photometry on this and also spectra to see if we can find more of this metal pollution, really trace how basically planetary system remnants around white dwarf stars get destroyed and get accreted onto the white dwarf. And also, of course, would have been great if we could have seen possibly an infrared signal where we see the light emitted from the dust. All right, so that brings me to the end of my talk. I'm a little bit early, I see, but I think the main takeaway is that time domain surveys keep finding interesting objects in our galaxy. This includes not just things we know, but also things we might not have expected to find, for example, related to exoplanet science. It's also a lesson, at least my takeaway lesson from ZTF is that there's like many different data products, and all of the different data products are useful for different science cases, and they might also be useful for science cases that you might not have thought of. So I think it would be good not to just stick to a single pipeline, but allow users to develop their own different ways of analyzing images. Sorry. That's also a point. Humans are still better at finding anomalies than computers. We definitely want to discuss that further later. But me eyeballing this data is basically the way I found all these weird and very interesting things. And I haven't found an anomaly detection method that could actually identify anomalies that are also astrophysically interesting. Also, a lesson learned from this is that historical data, combining both infrared and optical data was very useful, and also having historical data available. For example, the CRTS data, which goes back for 20 years, was very useful to see if variability was actually new in the ZTF data or not. And finally, related to the cataclysmic variables, we're finding tens of thousands of these dwarf novae. We basically are struggling to keep track of them all and really find the interesting ones. So I think with that, I'll end my talk. Thank you.
time for questions. I see if we're first in some early career researchers first, if there are. Otherwise, I think Mansi was the first one.
Jan, the white dwarf discovery with the negative sources is great, and it's sort of for the alert brokers in the room. We shouldn't toss out things that are negative, right? I mean, that's the important lesson. The question I had for you was you were looking at the most extreme ones. Were there any R-core Bohr stars in the data?
Yeah, so I focused my work on the white dwarf stars because it's already way too much to deal with, but I actually did run this search on all stars, and there's also a lot of interesting stuff in there which I didn't show yet. But yeah, it's more work than I can handle, including R-core Bohr stars, but also other things.
Bryce?
Yeah, sorry about that. So I'm a solar system astronomer. So I'm interested in linking small body populations in our solar system with the small body populations around other stars. What information can you take from these polluted white dwarf systems that gives you the physical properties of the small bodies and their planet surrounding them?
Yeah, so I didn't go into all of the details of the analysis, but as I mentioned, these rocky bodies pollute the white dwarf, so we can get abundance measurements or indirect abundance measurements of these rocky bodies. Based on the orbital period, we can also infer an average density. For example, the 5.9 period object probably has a density of more than 5 grams per cubic centimeters. Otherwise, it would have been tidally disrupted already. So we can already tell those things. It would be very interesting to learn what actually the parent orbit is, if these things originate from far out of the system and then are disrupted close to the white dwarf and circularize quickly. That's something, unfortunately, we cannot tell very easily. So there's definitely limitations here.
There was some there, no? Ryan?
Yeah, thanks for the nice talk, Jan. So I have a question on the disappearing white dwarf.
Mm-hmm.
So for things like luminous red novae or the subluminous red nova, which is the planetary engulfment, you see an optical peak and an infrared and mid-infrared peak. But for this thing, you see an optical dip and an infrared peak. So what's causing the difference there? And should there be an optical peak there somewhere that's consistent with some accretion of some material?
Well, so these are really low energy events. For this one, the infrared flare was way too faint to do any spectral analysis, but there's other white dwarfs known where we do see some a brighter infrared signal, and in those cases we see that the dust temperature is still very cold, so you really wouldn't see that in the optical.
Okay, thanks. And then have you looked at Sphere X to see if there's any mid-infrared spectra of this?
That's the difficult thing about doing white dwarf science. They're all very faint.
Okay.
Yes, there's some. That was the person.
Thanks. Very nice talk, Jan. I was just curious, how did you establish that these are white dwarfs? Were you cross-matching with a white dwarf catalog or?
Yeah, sorry, I should have mentioned that. Yeah, I took the Gaia white dwarf catalog. So these are from parallax measurements. We know that these are white dwarfs.
Okay, gotcha.
And we've got spectra for all of them as well. So, yeah.
Okay, cool. And one thing regarding how you filter, so how did you get rid of the moving objects? Or did the catalog cross-matching help?
High proper motion objects?
Yes, exactly, yeah.
Eyeballing it.
Okay.
So yeah, there's definitely things that can be fixed with machine learning, because it is a very easy thing to see by eye, but yeah, I just thought, well, it's just quicker for me to do it by eye. But yeah, if you want to do this with Rubin, definitely machine learning would help.
Thanks.
So is there any rate estimate based on observations or theoretical predictions for such an event?
I did calculate the rate based on how long ZTF observed. I don't think there has been any theoretical prediction how often this should happen. I think we do know that about 25% of all white dwarfs are polluted, but of course the pollution can, for some white dwarfs, it can remain thousands of years. So it's pretty uncertain how often you actually predict to find events like this. So yeah, I think it's very exciting with Ruben that because these events last so long, it should be easy to find and you can get a much better rate estimate with the future Ruben data.
I actually have a question about that. So is there gonna be negative alerts in Ruben?
I think the answer is yes, right? Well, yeah. At least I'm counting on it. Let's put it like that.
We're out of time, so keep that for maybe the discussion later. And I think we're moving. Thank you. Let's thank Jan again.